I'm Ken Leung from the Bishop Hall Jubilee School. Today I'll be talking about the summation of fractional parts. The PowerPoint is divided into two sections. For part 1, that's the distribution of sequences modulo 1. So let's begin with some definition that the fractional part of x is defined as x minus the greatest integer which does not exceed x. And we usually denote it as x in the curly bracket. For example, to compute the fractional part of pi, we chop off its integral part 3 and get roughly 0.14. So for the history, the fractional part sums have been studied by many mathematicians since 100 years ago. For instance, this theorem first stated by Lurch and later proved by Hardy-Littlewood that if alpha is an irrational number with bounded partial quotients, then the fractional part sum is roughly a half times n with the error term of order log n as n tends to infinity. It's not really surprising because the fractional part must lie between 0 and 1, so its expected value should be a half. So that's a reasonable main term. So for example, the golden ratio phi is satisfy the condition since if it is expressed as a continued fraction, the sequence in the red color, that's all 1, and that's a bounded sequence. So, but instead of studying the fractional part sums of linear function, I work on the nonlinear concave function. Before I talk about my work, I shall introduce another important concept, that's the discrepancy. The discrepancy dn is defined as the soup of the difference of the ratio of the number of terms lying between alpha and beta and the expected ratio, or you may say the probability, and that's beta minus alpha. So roughly speaking, it measures the deviation of a sequence from an ideal distribution. The discrepancy is closely related to the fractional part sums because of this Cox-Merz inequality. And more specifically, we have the error term of the fractional part sum is bounded by the number of terms times the discrepancy dn. So, the functions I studied are described by the theorem of Niederreiter that if f is continuously differentiable and satisfies certain growth conditions, then the discrepancy dn is that big old thing as n tends to infinity. Therefore, it follows at once from Cox-Merz inequality and the theorem of Niederreiter that the fractional part sum is roughly a half times n with the error term of big O f n plus 1 over f prime n as n tends to infinity. But however, the result is ineffective that the implied constants hidden in the big O notations here are unknown. So what I have done is that one of the implied constants is now made explicit, and so that's 1 plus epsilon here in the red color. There are two main ingredients in proving this theorem. The first is a lemma. For convenience, I shall call it as the generalized Gauss lemma. And the second one is the Euler-Maclaurin formula. Originally, Gauss gave an elegant proof of the law of quadratic reciprocity by counting the lattice points under the line of equation y equals p over qx, where p and q are some odd primes. So I'm inspired by his lemma and generalized it as follows. But despite its simplicity, the lemma can be very effective once fn grows much slower than n as n tends to infinity. So instead of studying the fractional part sum, instead of studying the sum on the left-hand side, we can study the sum on the right. So the second one is the Euler-Maclaurin formula, which allows us to convert the summation into some simple integrals. Here is the flow of the proof that we first prove the theorem for smoother functions and a subsequence of sufficiently large integers. Then we extend our conclusion to all sufficiently large integers by filling the gaps between the consecutive terms of the subsequence with the trivial bound. And at last, we show the theorem is still true for original functions. Moreover, if the function is even 3 times continuously differentiable, then we can take more terms in the Euler-Maclaurin formula and get a smaller error term. So here the implied constant is smaller, and that's 7 over 12 per epsilon. In fact, there are some common functions satisfying the conditions. Here are the two corollaries for some small powers function and certain powers of log. Okay. So let me talk about an application of the fractional part sums, since as I've mentioned, the Cox-Merz inequality tells us that we can derive the error term of the fractional part sums from the discrepancy. So what I've done is just in the opposite direction. This is the lemma by myself, and it follows from the lemma that we can give an elementary proof to a stronger form of the theorem of Niederreiter that I have just mentioned. Okay, and so that's the first theorem here, and the implied constant is explicit now, and that's 3 over 2 plus epsilon. if the function even has a non-negative continuous third derivative, then we can have a slightly refinement that's 1 plus epsilon there. So now let's come to the part 2, that's the distribution of sequences modulo integers. Here are some definitions of the quadratic residue. Reduced residue, which I think is a better name given by Montgomery and Vaughan, and the final function defined by myself as phi alpha n is the number of reduced residues between alpha and n, including alpha. So that's basically a generalization of the Euler-Stochern function. For the distribution of quadratic residues, we have these exact formulas for the number of quadratic residues modulo prime p in a certain interval of length p over 3. And then we have a similar result for the interval of length p over 4. So these formulas involve that one thing, and in fact that's a special value of the Dirichlet L function there. So it's very difficult to be computed, but at least from the non-vanishing, or you may say the positivity of L1 chi, we can have these well-known corollaries that we know there are more quadratic residues or less residues than non-residues in a certain interval. Okay. For the distribution of reduced residues, I have to first apologize that the following theorems have been proved by HLMA. So I have to give credits to him, but fortunately our expression and approach to theorems are quite different, since my argument is still based on the fractional part sums and it's rather indirect. So in my expression, that's the lambda n, that's the Liouville function, and omega qn defined by myself as the number of distinct prime factors of n which does not equal q. Here is the proof sketch for both quadratic and reduced residues. So because their proofs are very similar, so that's basically killing two birds with one stone. So for each case, we consider an auxiliary sequence AM with x terms. Then since the distribution is more or less the same as the distribution of the quadratic and reduced residues, and the fractional part can serve as the indicator function here. So now our goal becomes finding the number of terms not less than 1 minus over q, where q equals 3 or 4. So we'll have this equation 1 here. So on the other hand, since the fractional part function is a periodic function with period 1, so we can do a Fourier transform so that so it is expressed here as some sums of the exponential function. And okay, hence on the other hand, we have the fractional part sum is roughly a half times x, where x is the number of terms, with the error term involving the sum of the exponential sum. That's the skn. For the quadratic residues, that's the Gauss sum there, and for the reduced residues, that's the Ramanujan sum. So and finally, by combining equation 1 and 2, we have that the number of terms not less than 1 minus over q is roughly x over q. Of course, we have the exact formulas, but not these asymptotic relation. So we can deduce our theorems at once. So let me talk about average orders and partial sums. It's because since we have just defined a new function phi alpha n, it's natural to consider its average order, which is defined as the partial sum of the arithmetic function divided by the number of terms. Then we have these simple theorems, and the average order is not surprising because each for the phi 2n over 3n is just asymptotic to the Euler-Stochern function divided by 3. So but we can refine the theorems slightly by an equivalent form of the prime number theorem, which involves the summation of the Mobius function, so that we can have a more explicit relation between the partial sum of the new defined function and that of Euler-Stochern function with a smaller error term. So that's the little o x log x as x tends to infinity. So that's all what I want to say. Thank you.